Ladies and gentlemen, thanks for having me here today. It's an honor to present to you the results from the data structure and data use groups. Actually, I am only the vessel to talk about this today. This is the work of many great minds that took a long time and lots of work to work on this topic. And it's a great honor for me to present here today, but please remember this is a group effort and it wouldn't be able to have performed this without the help of all of these people. I myself have nothing to disclose. This was a group work, as I said, of medical personnel, industry personnel, and scientific personnel, engineering personnel, to create a common foundation on which we can build in the future. If we want to look at how data use and data structure play together, then it's of course important to understand that usually we start with a research question, a data use case, so to say. And based on what we want to have answered, we define the data structure. We have requirements for the data structure that we then start collecting data. We start sorting that data, organizing it. And once we're done, that data structure enables us to answer that research question that we have. The problem comes if we want to use data in the long run. For example, we start to look at different research questions and different use cases in the future, or we want to collaborate with different partners. Because we did not have that requirements collection step in the beginning, then the data base is limited in what we can do with it and helps us answer it. So this is a problem that everyone probably has run into already, or even runs into regularly as we do. And this way, today, I want to have a look together with you on how we can look at data use holistically and how we can use that to inform data structure holistically. So this part has presented at the SAGES workshop this year by Pietro Mascani, Armin Madani, and Nicolas Padoy. I am going to show their findings to you today on their behalf. What this group looked at was to create a matrix of stakeholders and use cases. Basically, have stakeholders on one axis, users on the other, and use that to create a map that we can use to analyze the needs that we have in a research setting or in a medical setting. And the matrix they came up with basically is this. This is a blank slate that you can use to analyze your project. We have patients in civil society, surgical teams, researchers, scientific societies, editors, healthcare institutions, medtech companies, health insurances, and public institutions on the stakeholder axis. We have clinical, research and development, education, medical legal, quality assurance, and marketing on the users axis. And I don't have the time, unfortunately, to go completely into detail for one of these analyses, as I only have 15 minutes, and this talk is going to be a tour de force anyway. But what I can do is I can do a little example on a use case, which is a group of surgeons and engineers working in collaboration with SAGES would like to start prospectively collecting surgical video data to engage in a multi-center study using artificial intelligence to improve patient care and physicians' workflows. The hospitals are located in the US, Germany, UK, France, and Canada, an international setting. So first off, the surgical team might look at the clinical uses and identify a need that they want solved. Researchers might look at the research and development area, find out what is needed technically to realize those needs. A group like SAGES might be used to transfer that, validate the needs, and make sure this is actually not just a local need, but a global need that needs to be addressed. For prospectively collecting surgical video data, we need to look at clinical patient consent. We need to look at ethics approvals. The multi-center study using artificial intelligence requires an analysis development, publication strategies, data for publication, and a strategy for social media disseminations. Data can be disseminated in social medias, as many YouTube channels have shown very effectively. To improve patient care and physicians' workflows, we need again to look at consent, decision support in the clinic, raising awareness, workflow optimization inside the clinic and healthcare institutions to transfer our work, fundraising and sale by medtech companies to get production working, risk mitigations from health insurances to make sure that what we do is insured, and in public institutions find market approval, for example by the FDA, so we can actually move our product to the market. What that entails, if you really look into it, is shown in this matrix. I don't expect you to just look at that and understand it. I couldn't do it, at least. This is a lot of work, but it shows the many, many things that you have to consider when you want to start collecting data in the long term. As if that's not enough, we decided, or the group decided, that 2 axes are not enough, use case and stakeholders. We should actually add a 3rd axis to make this a 3D matrix, and that matrix is guiding principles that we want to use. These guiding principles include accountability and transparency, commercialization and monetization, confidentiality and privacy, equity, justice, inclusion, collaboration, innovation, harmlessness of our product, and the public interest, of course. Why do we need that? Because these guiding principles are important if we want to share data and if we want to use data for future use cases. Surgical video data primarily collected by a stakeholder today may be accessed by multiple stakeholders for other users in the future. And that surgical video data should be used according to a set of guiding principles shared among those stakeholders. That means, in the simplest of terms, don't do evil, make sure that you know what your data is collected for, and then ascertain that it's not used for anything contrary to your principles. The data governance should then account for primary versus secondary use of surgical video data, differential access to metadata based on who sees what, depending on their needs, and the tracking of surgical video data access as well, so we know who has accessed what when. And finally, data structure requirements change according to the stakeholder and the use case. That's why it's important to do this exercise to make sure that your data structure is suitable for what you want to do in the future. So now that we've finished data use, let's look at the second part, data structure. This again is part of the SAGES meeting and was presented there by myself on behalf of the working group data structure, which is listed here. The relevant content for data structure is more than you might think at first. Let's start from the bottom up. We have the data format, which is the internal structure of the video file. We have metadata format in organization, which is the structure of data directly related to that video file. We have data structure in clinical reality, which is the effect of clinical application on the structure of data and metadata. And finally, we have the step of drawing conclusions on all the data that we collected, which in the end, we hope to enable bias-aware surgical data science. Biases? What do biases have to do with data structure? And the answer is, unfortunately, a lot. Let's look at that first. A bias is a disproportionate weight in favor of or against an idea or thing. And we focus on 2 types of data-related biases here, the selection bias and the confounding bias. The selection bias has as a source the data collected is not representative of the whole population, and the consequence is that the algorithm is biased towards the training population and it does not generalize. This has real world consequences. This study here showed gender imbalance in medical imaging datasets produces biased classifiers for computer-aided diagnosis, meaning here male and female populations were not equally distributed in the population, and those algorithms were better performing on the male population and on female population, which is something that we do not want, obviously. And the second bias I'm going to go into here today is the confounding bias, and the confounding bias is described as a mixing or blurring of effects that occurs when an investigator actually measures the effect of another factor instead of the one that he wants to measure. And again, this can have drastic consequences. In this case, this is a paper published in Nature, which showed that during the corona pandemic, where everyone wanted to detect COVID-19, many papers used the pneumonia dataset of Kermany et al. As a control group. They commonly fail to mention that this consists of pediatric patients aged between 1 and 5, so children. Developing a model using adult patients with COVID-19 and very young patients with pneumonia is likely to overperform, as it's merely detecting children versus adults. That's right, the algorithms learn to decide thoracities and tell these apart from children and adults, not COVID-19. So, in conclusion, no valid conclusions can be drawn from AI studies if biases are not properly addressed, and the data collection and sharing and reviewing process has to pass scientific rigor from both groups. Let's look at data structure and clinical reality next. The role of video is steadily increasing in OR. There are more types of video than ever before. We have endoscopic video, ultrasound, body cameras, video from the operating room, and additionally there's a shift from short clips to operations spanning movies. But at the same time, standardized video exchange is rare today, and video is rarely acquired or stored in a structured manner, or even worse, it's routinely deleted to save space. Additionally, time synchronization is unavailable often, and synchronization data is rarely stored. What that means is that if we want to use, for example, video data and other data from the operating room, for example, data from the anesthesia machine, that's very difficult after the fact because we do not know at what time that data came in. So the proposal here is that we should strive for universal support for video exchange and standards and synchronized clocks in the operating room and recorded data. And finally, we should start to view video as a part of the patient record in the long term. Finally, let's look at metadata format and organization, the structure of data related to the video file. And today, video data is disconnected from metadata. It's hard to leverage additional data, and additional data is the key to making video valuable. On the other hand, metadata storage today is usually ad hoc data organization, non-standardized, inconsistent metadata and annotations are the norm, which means it's hard to share data with your contributors and collaborators. The proposals here are: we should start to enrich metadata with info on patients, surgical team members, devices, protocols, annotators, and the context in which they have been recorded. And we should establish a vocabulary to facilitate data sharing and joint understanding and facilitate data searching and accessibility locally. Finally, we should establish a joint infrastructure for data sharing between all of us so that allows us to collaborate more easily in the future by agreeing on these terms. At the very last, finally now, let's look at the data format, the internal structure of the video file. And this is where it finally becomes really nerdy. Please bear with me. The video container itself contains data streams, so one or more video streams and audio streams, which are encoded separately. And that encoding makes a difference because it's always lossy, means or usually in many practical cases lossy, otherwise the files are just gigantic. And additionally, there's metadata inside the file, embedded in the file. And it's important to understand that as well, because this embedded metadata can cause unintentional data leaks if you are not careful. And those together are contained inside the video container. So that's the file that you see on your drive, the MP4, WebM, or AVI file. Additionally to that, we usually collect external metadata like title, author, etc., which is stored in a sidecar or database. There's a number of video metrics that we need to talk about as well. The resolution, which is just the number of pixels width by height. A height of 720 pixel is usually called high definition, but most computer vision models today resize that to a much smaller resolution. For example, 224 by 224. Due to performance reasons today, this will get larger in the future with stronger machines. The second metric is the frame rate. Under 12 frames per second, there's no motion perceived. I understand that I'm coming close to that with this presentation. My apologies. 24 frames per second and higher is smooth enough for humans. I do this in air quotes because there's some discussion regarding that. Most computer vision models today still use only 1 to 2 frames per second, again, due to performance reasons. Our proposals here are: avoid transcoding if at all possible. Each transcoding step introduces quality loss, creates artifacts, and these artifacts can be detected by algorithms. So we have a COVID situation, like before again, where an algorithm tells apart transcoded videos from non-transcoded videos instead of the target parameter. Remove excess metadata that's internally stored. This is a data leak. Move metadata into the external file where you can then control it properly. If transcoding is needed, go for maximal compatibility, either an MP4 container, which commercially used requires a licensing fee, but allows you to embed it in DICOM, which can help a lot. Or if that's not an option, go for WebM container VP9, which is free and still widely supported. In summary, look at your data use holistically to decide how your data structure should be like to enable your future use cases. Here's a metrics that you can use for your own analysis. and use that analysis to inform your conclusion regarding the data structure. The final goal should be to understand the long-term needs of your use cases and design your data structure accordingly to generate a lasting impact and to enable surgical data science in a bias-free manner. Thank you very much for your attention. Enjoy the conference. It was a pleasure speaking to you today.